Hi there, and welcome to my lesson on Newton's laws of motion. So this is where we're going to start talking about forces, and we are going to define a force and talk about all three of Newton's laws of motion. Now, in the textbook that I use to teach with, all three of Newton's laws are divided up into three different chapters. I believe it's chapters 4, 5, and 6. However, I am going to combine those things into one unit and one unit test. So this is going to be my overview, and then I'll get into more specifics as we move along. So let me first kind of deal with something that is a little bit of a pet peeve of mine, of people misunderstanding the idea of what a theory and what a law is. And this is a good time for me to talk about that. So a theory is something that explains why something happens. A law explains what happens. So typically we'll have a certain law, a scientific law, that is just there to explain the repeatability of something. I can't talk. And so something like the law of gravity. So we have a law of gravity, which basically says that when we drop an object that is a certain distance away from the Earth, it will fall at a very specific, predetermined, predictable rate. And so that rate is 9.8 meters per second squared. And so, if we went to a different planet that was larger or a larger size, we can predict very precisely exactly what the acceleration of gravity would be at that surface of that planet, or at some distance from that planet. And that's the law of gravity. But it makes no attempt at explaining why gravity happens. And so the theory of gravity is something very different. That is making the attempt of explaining why it is that there's this apparent pull of gravity towards the surface of the Earth. And that is something that Einstein had originally proposed, of describing gravity not so much as a force, but instead the curvature of the fabric of space-time itself. And that's something that we will get into another time. So just understand that there's a difference between these two things. A theory explains why it happens, and the biggest misconception that people have is thinking that a theory will, as it becomes more and more proven, it becomes something else over time. And that is not the case whatsoever. A theory is always a theory. A theory does not become scientific fact. That's just not how it works. So I just wanted to clarify that, just so we can move forward and not have certain misunderstandings. A little bit of history, not a lot. Copernicus was the first person to think of the heliocentric model of the solar system, and his idea was that it was a sun-centered solar system. And so he had, in his idea, of course, he had the sun, big bright sun, and then of course there's all the planets that go around it. So you've got Mercury, it goes around in this elliptical orbit around, and then you have Mercury, Venus, and Earth, and so Earth would be out here, and it goes around in its own orbit. And what's interesting is that all the planets go around along the same plane. If you were to kind of tilt yourself at 90 degrees to this circle, so you've got these orbits, and then if I were to take that plane and you were to get eye level with it, all of the planets are pretty close to the same plane of travel, which is quite interesting. But Copernicus was the first one really credited for, in the modern world, to express that the sun is the center and not the Earth. Those who believed that the Earth was at the center really did so much for religious reasons. Galileo had reiterated this sentiment from Copernicus, although they both actually had something in common. They both kind of made these statements a bit later in life, especially Galileo. He had actually, I believe it was on his deathbed, if I'm not mistaken. No, Copernicus did it on his deathbed, and Galileo had published his book that basically said that the sun was at the center. However, this was not something that the church was very happy with, so they put him under house arrest. Now, keep in mind that the church liked Galileo, and so had they not liked him in the first place, his punishment probably would have been a little bit worse. So when he was under house arrest, he started to observe the stars. He had a bit of a hobby of making telescopes, and he started refining his technique of making these telescopes and started making much greater discoveries about the heavens, the planets, their movements, and then later in life his discoveries of and observations of the sun. So he discovered sunspots, things like that. So something that he said is that a force is not necessary to keep things in motion. So he recognized that the Earth was actually traveling, right? So let's just say it's traveling in this direction at that moment in time, and then when it gets over here, it's traveling in that direction at that moment in time. And he recognized that if the sun wasn't pulling on the Earth, that the Earth would just continue to move in that direction forever. But because there is a pull by the sun in this direction, that it alters its path at just a constant rate. So when it's over here, it's being pulled that way, even though its velocity is in that direction. He was not so much concerned about the how, but or he was concerned with the how, not so much the why. So that whole theory and law issue. He the story goes that he dropped various objects from the Leaning Tower of Pisa. He's not really the one who did it, and it was never really the Leaning Tower of Pisa. He got credited with doing this experiment post-mortem by his apprentice, who wrote a book and kind of gave him credit for doing these things. But nonetheless, he did do some other various experiments, like he had these ramps that kind of had this sort of like U-type shape, and he would roll a ball, and he noticed that the ball would go down one side and then it would come up and go just as high on the other side. Kind of showing that whatever gravity like kind of does here, it sort of like undoes on the other side, and he did it with various sized objects and realized that mass was not really relevant. Okay, let's move on. So big misconceptions is the difference between mass and weight. Mass is a measurement of the amount of matter in an object. So it is measured in kilograms. Kilograms is in fact the SI measurement for mass. So we want to always use SI measurements in physics when possible. So that is going to be meters, seconds, and kilograms, basically, as our SI, our basic SI units. Now I do realize that kilo, right? Why does it have that prefix if it's an SI unit, if it's like the base unit? And there's a really good video that Veritasium had done that I'll probably post that kind of explains why it is that it's kilograms rather than grams. But basically grams was too small, so we made it kilograms as our base, as our SI unit. Weight is different. Weight is actually literally the force of gravity. So when you say the word weight, you actually mean the force of gravity. So if you were to go to the moon, and this is a very common question, if you were to go to the moon, suddenly just be transported there, would your weight change? Would your mass change? What changes and what doesn't? And so if you were to be transported to the moon, the stuff that makes up your body does not increase or decrease. So your mass would stay the same. Your mass in kilograms. Okay, if I'm 75 kilograms, I would be 75 kilograms on the moon, on Earth, or out in space. However, the force of gravity is less on the moon because the moon is smaller and the pull is not as strong. So typically it's about 1/6 the strength of that of Earth. So if I were to go to the moon, my weight would be 6 times less than it is here on Earth. If I use the acceleration of gravity as being 10 meters per second squared, which, 9.8, 10, close enough, my weight, or I usually like to express it as the force of gravity, little subscript g, is equal to mg, where m is your mass in kilograms and g is the acceleration of gravity measured in meters per second squared. So here on Earth, if my mass is 75 kilograms and the acceleration of gravity is about 10 meters per second squared, then that means that my force of gravity, or my weight, is about 750, well, what are the units? I'm taking kilograms times meters per second squared. So those are the actual units. It's kilograms times meters per second squared. However, there is a bit of a shortcut here. Rather than having to say this very strange looking and strange sounding convoluted unit, instead of saying kilograms times meters per second squared, instead we just say newtons. Capital N for newtons. So I weigh 750 newtons. When we say I weigh 750 pounds, that's not quite entirely right. And if I were to ever say that I weigh 75 kilograms, that would definitely be wrong. My mass is 75 kilograms. My weight is 750 newtons. So do not confuse mass and weight. They are definitely different. A force is a push or a pull, and a force is required to accelerate an object. It is a vector quantity, and as I said, it is measured in newtons. A net force is the resultant of all the forces that are being applied. And so what we often will express the net force as is we will say that we'll express it as this. This is the sigma symbol. Sometimes it has these little like sort of hook things on the end here. And so the sum of all forces, actually I'll get into that. That's Newton's second law. But I just want to express that this is the symbol for it, that it is sigma F, that this is the sum of all forces, which is the same thing. It is the same thing as to say the net force. So the net force, the sum of all forces, the resultant force, saying each of those three things are all the same. So after everything is said and done, after all forces have been added and subtracted, your net force. So for example, if you are sitting down at your computer watching this on the awesome screen, like, here comes there's the rays of light coming towards you, and there is a stool here that you're sitting on, or a chair, or whatever it might be. So there is a force of gravity acting down. That force of gravity is mg, as we said in the previous slide. But there's also a force acting up on you, right? That's from the stool acting onto your bottom. And so that is what we will call the normal force, and we'll get into that in a moment. But the force acting down is equal to the force acting up. I know that because you're not accelerating up or down. And so you are in equilibrium. Those forces are equal. Your net force is equal to big fat 0, goose egg. Friction is a force that opposes motion. So when you try to slide an object along a surface, you have this friction force that slows you down. And I'll get a little bit more in detail in that in a moment. But if you are sliding into a certain direction, then, and I should use the word sliding, not moving, but if you are sliding into a particular direction, friction is going to try and oppose that motion. Tension is a force along a string. So if I have an object that is hanging by a string, then we have a force of tension that is acting upward. And then we would also, acting onto this object, we would have a force of mg acting down. And so if the object is not accelerating, then the force of tension acting up would be equal to the force of gravity acting down. If the object was accelerating upwards, then perhaps I could express this force of tension as being larger. I'll make the object bigger too, sure. So if this force becomes larger yet, and we usually would just express that with a longer arrow, right? Let me go ahead and do that. I'll just make this arrow a little bit longer. And so if this force is larger, then it would accelerate upwards. And then equilibrium, as I said, is when the net forces equal 0. So if these two forces are equal, then the net force would be 0. The system is in equilibrium. I talked about the normal force. The normal force is a force that acts perpendicular to the surface. So in my example of the person sitting on a stool, right? So here's the stool, here's the person sitting on that stool. They're happy about it. And the force of gravity of this person is acting down. And then because the surface of this stool is basically a fairly horizontal surface, then the normal force would be straight up. However, if we look at an example where there's some sort of inclined plane, oh look, there's a snake. And so we have a box acting on this inclined plane. The force of gravity acting down is mg, and then the normal force acts perpendicular to the surface. And so since the surface is at this angled slope, then the normal force must be acting perpendicular to that. Now, if you can imagine that this slope were to increase greatly, more, then this normal force would be decreasing actually, to the point where it's barely making contact with that surface, and obviously the object would slide at some point. And so the normal force is perpendicular to the surface. However, for our purposes, almost always we will treat it where it's a horizontal surface, and so the object sits on there and the normal force will just be simply straight up and will be acting in the opposite direction from gravity. This is our most typical example. Inertia. Super important concept of inertia. So inertia is the tendency of an object to resist a change in motion. So if I have an object, if it has just a little bit of mass, right, I'll put some hash marks in here to represent its mass. If it has a little bit of mass and I give it a push, it's going to resist now suddenly moving. Or what if this object is already moving with some velocity? If it is moving with this velocity and I want to either speed it up or slow it down or make it change direction, I just want to make it turn, in any of those cases, it's going to resist me doing that. When I go to push the object, I would feel its resistance. Now, if I were to take another object and I make this a much more massive object and I give it the same velocity, it's a constant velocity, and I try to give it a push, clearly this object is going to resist either slowing down, speeding up, or changing direction that much more. And so keep in mind, inertia works whether the object is moving or not. The more mass an object has, the more inertia it has. In fact, inertia and mass really are the same thing. So if I have this object, and let's just say that it has 10 kilograms of mass, so that's its mass, then I guess I could kind of say that it has 10 kilograms of inertia. But that's just not really the mindset. You see, inertia is the qualitative description of this object's ability to resist a change in motion, versus to say the word mass, that is the quantitative description of what this object has. Okay? These really are the same thing. This is more the qualitative description of it, and this is more the quantitative expression of it. And let me get into Newton's first law, and I think what I'm going to do is I'm going to probably just end on that, and I'll get into the other laws later. So Newton's first law of motion states that an object in motion stays in motion, and an object at rest stays at rest unless acted upon by an unbalanced, non-zero net force. And yes, I really do want you to have the wording exact on this. This is also known as the law of inertia. So this is effectively what I was just stating about this whole idea of inertia. This is just putting it in words, and this is basically just a restatement of what Galileo had said. Okay, so this is Newton's first law of motion. And I think that maybe I can go over one conceptual question with you. Let's do this. Here we have an example where we have a rock hanging off of a string from the ceiling, and then from the bottom of the rock we have another string, and you're pulling down on it with your hand. Now if you were to pull down, okay, so you're going to pull down on this string, and you pull gently, okay, you pull a little bit harder, a little bit harder, a little bit harder, and the string of course has some elasticity to it, and it's going to stretch a little bit, and it'll stretch to a point where eventually it just snaps. So when you pull down a little bit harder, a little bit more, a little bit more, a little bit more, and eventually one of these two strings snaps and breaks. Which one breaks? Think about that for a moment. What's happening with the forces and which one breaks? So, do you have an answer? The first one, okay, the first one up here, this is string 1, let's say, will break. Why? Because acting on this string, you have a force of gravity acting down. Okay, you have a force of mg acting down, and then also acting down, you have the force of tension from down here, right? So this is, let's just call this force of tension 2, and this is force of tension 1. So the force of tension acting up, right? So we have, basically we're going to say this, the sum of all forces equals, let's see what we have here. So we have forces acting down and forces acting up. So we have a force of tension acting up this is the force of tension of object 1, or string 1. So I have a positive force of tension from string 1 acting up minus the downward, right? We're going to treat downward to be the negative direction. So minus mg, and also minus the force of tension from string 2. So this whole thing equals 0 because the thing is not accelerating, right? This whole thing equals ma. So we have a force of tension acting down, we have force of gravity acting down, and clearly this force of tension must be larger than this force of tension because the gravity is helping this one, right? Gravity is helping this force of tension act down. So the force of tension is going to be greater on this one. Clearly it snaps and breaks first. However, what if we were to pull quickly? What if we were to, like, just as quick as we can, just whoop, and we just pull down very quickly? Does the top one still break? And the answer to that is no. That the bottom breaks first. But why? The bottom one breaks first because this object has inertia. If you pull quickly, the string here stretches because this rock resists moving and accelerating that quickly. Since it resists accelerating quickly, this string will never get that tension. It will never have a chance to stretch because in order for this string to stretch, this rock has to move downward. Okay, it would have to move downward in order for this to stretch. But since it has inertia, this string will get tension first since this rock will resist moving. So if you were to pull very quickly, the bottom one will get tension first and it will break before this one ever gets any tension at all. So here's a good application of inertia in action. Okay? Another good example of inertia in action might be something like this, where you have some sort of platform, and if you were, let's say for example, you had a person on a skateboard standing on this platform. Right, so there's the skateboard with the wheels. And can you imagine if this platform was like the back of a truck or something, and you made the truck accelerate? Do you recognize that this person has inertia and they're going to stay put? You just slide it out from under them. It's kind of like that whole thing where you take a tablecloth and you pull it out from underneath all the plates. So actually, it turns out that the heavier the plates, the better that trick works. This person, the heavier they are, the better this trick works because the more inertia they have. Or if this person was standing on the back of the truck and the person are moving together, then the truck suddenly comes to a stop. Well, I feel bad for him because you see, if this is the truck bed and they are moving towards the left, he is going to continue moving towards the left until he hits that thing right there. He's in motion, he will stay in motion. So that's why if you have like a construction vehicle, a van with lots of construction materials in the back, you really often want like a gate or something in between you and all of those materials, because if you come to a sudden stop, all of the stuff that is in the back of the truck is going to continue moving until it hits you in the back of the head. I've had it happen. So there's a couple of lessons and applications of Newton's first law, and I think what we'll do is we will tackle the rest of Newton's laws another time. I hate separating them because they weave in together so much, but let's just kind of leave it at that for now, and so let's just kind of think about that whole thing of like Newton's first law: objects in motion stay in motion, object at rest stays at rest, unless there's some sort of net force that acts on it that causes it to accelerate. So with that, I'll leave it, and we'll talk again. See you soon. Have a good one.